All right, good afternoon. So we are doing the Lab 4 primer, which will also help us prepare for Quiz 3 because we'll be messing with processes. So this will essentially be able to write some useful program that will essentially be Lab 4. Hopefully we can do it by the end of today. And that should well prepare you for Lab 4. So this is mostly you guys programming because I'll show you the tools and you guys will come up with the solution and it'll be lots of fun. So here's our task for today. We want to send and receive data to a process. So we want to actually do some IPC. We want to communicate with some processes. We don't want to do the lame thing of we write to a file and then we read from a file. We're going to do some actual communication while both processes are alive. So our task for today, we want to create a new process that launches whatever program we give it as the command line argument, and then we want to send the string testing with a new line to it, and then we want to read any output it gives, and that's it. So we want to send data to a process, get data from the process, and turn it into let it execute a different program. So we're going to need some APIs. We'll whirl around through them. Our first new API is called pipe. It is kind of a one-way communication stream. So here, int pipe, and it takes an array of ints that are just two file descriptors. So it's going to create two file descriptors. So it's a C wrapper for a system call. So it returns 0 on success, -1 on failure, sets error no, kind of what we're used to. So it's a one-way communication channel using file descriptors. So again, I said it gives you two file descriptors. So it gives you file descriptor at index 0, which is the read end of the pipe, and a file descriptor with index 1, which is the write end of the pipe. So the way this works is any data you write to the right end of the pipe pops out of the read end of the pipe, and you use the write and read system calls just on any old file descriptors. So you can think of this pipe as a kernel managed buffer. Again, any data you write to the right end is going to pop out of the read end, and we'll be able to use this to communicate. Yep.
So both processes have access to this pipe?
So if you want to communicate, they're going to have to both have access to it, and that's what we're going to solve. So if we fork, it's a copy, right?
But they're not exactly this. So if you change one, the other one doesn't actually change.
Yeah, but if you create it and then fork, it's a copy at the fork, right?
So
What?
Sorry, the screen was shaking.
Oh, it's going to shake all day because they're jackhammering.
Copy at the fork, so there are copies and then you fork, but this copy after you make a change, it will change the one after.
Yeah, so anything you write, it doesn't matter what process has it. As long as they have that file descriptor, if you write to the one end of the pipe, you can read that data from the other end of the pipe.
Oh, so it's essentially just like a copy that looks like a voodoo ball kind of, where if you do something to one, it affects the other.
Yeah, but the kernel manages the buffer for you, so you can use it to communicate between processes, and that's what we'll do. Yeah.
Oh,
That's the same question? Okay, we'll see how you use this. Yep.
you said it was a buffer, so how much size is it? Or is it dynamic? Or?
The kernel does it, don't worry about it.
Okay.
So it's a kernel managed buffer, there's probably a limit to it, but
And is pipe specifically for communicating between processes or
Yep.
files?
processes. So it's a file, it gives you two file descriptors. You write from one side, pops out the other end. That's all it does. You can use it in a single process, but at that point you are communicating with yourself, which is pretty lame, and we can do something better. Yeah.
If both processes can use this pipe, why is it one way? If both can read and write, why is it for one way?
So one way, meaning that if you write into it, it just comes out the other end, but you can't write and go the other way. So if you want to communicate in both directions, you'd need two pipes.
So, but both of the processes will have access to this pipe FD
Yep.
number.
Yep.
So that they can actually both read and write to each other, right?
They could, but if you want to communicate with them, one should be doing the writes, that's sending data. The other should be doing the reads, that is receiving data. Yeah.
So, continuation of the variable being shared between the two processes, wouldn't that mean like we can technically still communicate by like changing a variable in one process and then the other one can see the change, but like
You can't see the change after the fork, though, right?
you can't see it?
No, they're independent.
Oh, but they have both have access to this pipe like buffer.
Yeah, so file descriptors are kind of like pointers. So they're pointers to something that, whatever that file descriptor represents. So when you,
The file descriptor is shared between all the processes.
so when it copies, it's going to copy all the file descriptors as well. Yeah,
Where does the buffer exist
in the kernel.
in the kernel?
Yeah.
And that's a physical memory location.
Yeah, but the kernel will allocate that for you and manage it. Yeah.
Sorry, so if 0 is read and 1 is write, what is 2? Or is that like,
That's an array of 2 ints.
okay, so that's how you declare it, or?
Yeah, yeah. So that's the argument by it. Everything's 0 index. So if you give it an array of 2 ints, you have index 0 and index 1. You don't have index 2.
Okay, and so like you create it first and then you fork. And if you've done that, then the two processes after the fork have access to the same pipe. Is that the whole thing?
They can. So we're gonna do this.
Okay.
So we have a task today. Okay, second one, and then we'll throw it all together and have more questions. So we saw exec VE. It's kind of a pain in the ass because you need an array, blah, 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 and then you have to give like the whole path to a file. You can use exec LP to make your life a bit easier. So instead of giving a full path that starts with the slash, you just give it the name of a file, and then instead of an array, you just give it a bunch of strings for the arguments, and when you're done, you just throw null at the end. So this behaves the same way as exec VE, except it's a little more convenient. Under the hood, the standard C library is going to transform it to exec VE, so it's just to make it easier to write for you. So if it's successful, it doesn't return because it transforms this process and starts executing whatever the program is, and it's going to search for executables given some path environment variable that's default set for you. And this is how your shell would work if you just typed ls. So ls will find wherever that executable is. So it just gives us a little bit more convenience. All right, next API we're going to need in our collection is close. You close a file descriptor, so it returns 0 on success, minus what? Yeah, some aliens are attacking, cool. So close, it's another C function, 0 on success, minus 1 on failure, so that's error no. Closes the file descriptor for the process, so that's no longer usable, and the file descriptor is just a number, you don't know what it refers to. So it frees up the file descriptor, and it can be reused because the way the Linux kernel works is whenever it creates a new file descriptor, it's going to use the lowest number possible, and we kind of saw that way back in the day. Yeah.
So essentially, every process, if let's say process 1 file descriptor 0 is the same as process 17's file descriptor 0, right?
Yeah.
They both refer to the same thing.
Yeah.
Oh, so that's why we can communicate.
Yeah.
What is the quickest way to find the lowest one? It can't just be like an array of all the numbers, whether or not they're used or not. Just zoom through it and find the lowest one.
You can zoom arrays are fast.
I guess, but it seems okay.
Yeah, you can look up the kernel implementation if you want, but it's probably going to be just zoom through. Arrays are quick, and you don't have that many file descriptors anyways. Yeah.
So like if processes are just communicating through like a file descriptor,
Mm-hmm.
can someone write like malicious code and then they can just read from different file descriptors and maybe get like a communication?
Yeah, but your web server is just going to read any old data, right? So up to you to make sure the data is valid.
How is this different from like just creating a file, writing to it, and some other process read from that file? It's like the same thing, but
So this is direct. I'm going direct from one process to another.
But you're doing that through a file descriptor.
Yeah, but if I'm reading a file in my system, I have to do an open call, and it makes it a file descriptor anyways.
Right.
So, and then my program, my file descriptor could represent a network connection too. It doesn't, it's just, file descriptors are anything you can read and write from. That doesn't matter.
It's not like an actual file or something. Like
No, it's just called a file descriptor.
okay.
Just, file descriptor is just a number that represents something you can read and write bytes to. So we've seen, you're used to it being a file, but it can now be a pipe. It could also be a network socket, which you'll probably see-ish, but everything we learn, it's all the same. Yeah.
Sorry, so what was exec CLP doing again?
So it's just making our lives easier. So it searches for that file in your path instead of doing like /user bin ls. You just put ls there and it'll find it for you. So it's just making our lives easier.
So ls is using exec CLP?
No, so this is instead of exec VE. Remember we had exec VE before and we did /user/bin/ls. So instead of that, with this version, I can just put ls in this argument and it will find wherever that executable is for you.
So it has to search through all of your
So it's,
files?
no, so it searches for everything in this path environment variable, which that's like the default thing. Here we can see if we echo path, that's how your shell works and how everything works. So it's going to search it in that order. So
Well, what if the duplicates, it just runs the first one finds?
yeah, first folder it finds. So that's why they put like local before the like system one. So it would take any local changes before. But like your UG whatever system's going to do the same thing.
So isn't that like in a less efficient though, because you have to actually search for it rather than you know what the exact path that you're looking for is?
Yeah, but in my shell, if I do that, right, I don't give it the full path.
Okay, so it, okay.
So when I do this, my shell is essentially doing that. It's searching path to find ls for me.
So when you type in this command, effectively what you're doing is you're calling exec CLP with the name ls, and it just searches all of that for that ls code.
Yeah, the ls program, like the executable file, then it'll launch it. Okay, so that was close. All right, so our final APIs are Dupe, so we can screw around with the file descriptors. So Dupe takes an old file descriptor and a new file descriptor and makes both of them point to the same thing. So in Dupe's case, it just returns a new file descriptor on success, -1 on failure, sets error no, and then since it returns a file descriptor, whatever file descriptor it returns points to the exact same thing as the file descriptor argument you pass as old file descriptor. So, and in Dupe 2, you get to pick what the new file descriptor is. So you get to reuse new file descriptor. So if it's open and valid, it will go ahead and atomically close it and then replace it with, and then make old file descriptor point to the same thing as new file descriptor. And this this is why it's a different system call, because it needs to be atomic, because it's going to close and then it has to reuse that same number. So if it's not atomic, you might have another process come swoop in and steal that file descriptor number. So that's what they do. And yeah, any questions about that?
Wait, so in a regular Dupe, it says it copies the file descriptor so that old and new are the same, but where is the new?
It returns the new file descriptor. So both of these return the new file descriptor. And in the case of Dupe 2, you would,
Oh, so it just makes a duplicate of the current and then that one.
yeah, it makes a duplicate of old. And so in the Dupe case, it will return new. Well, in both cases, they return new. But in the first case of Dupe, you don't pick what the new number is. And in the case of Dupe 2, you get to pick what the new number is.
What if the new number is something else?
So it's going to close it first if it's valid. There's a question at the back. So we are going to use them to play around with the file descriptors. So we're going to do that now. That's everything we need to know to do our task for today. So
If we force a file descriptor to close and then cause issues for like another process.
we'll see. Oh no. Okay. let's get to it. All right, so again, here's our task. We want to create a new process. We want to receive any data it writes, and it's just going to write data as standard input. And since we can play around with file descriptors, we should have an idea what to do. And then last one, we want to send a string testing to that process. So what would our first step be here? Do we know how to create a new process? Fork, and then execute something? Exec feed, okay, let's start with that and then we'll work with the communication. We'll use LP. So here I have some placeholder code, and then I fork. So at the point of the fork, they're exact copies of each other, the only difference being the value of PID. So just to make things more readable, if it is greater than 0, it calls a function called parent, and then gives the PID of the child. And if it's the child, it calls the child function and passes in the first command line argument, which should be the program to run. So if we want to just run the program in the child, we can just do exec LP and give that argument to it, and it should go ahead and find it for us. So if we go ahead and compile that and do uname, so uname just outputs like the name of the system it is, so that's a good one to test. If I do that, it prints out Linux, which is exactly what you would expect if you just ran it. So why does it do that? What do you mean what's going on? So
Oh, so essentially you just run the program and the child changes to run uname.
yeah, so here the child changes to uname right after the fork, and the parent does nothing, and it just exits. Right? We're all good? So why do I see Linux on my terminal? Yeah, uname is running, but so when I start my program here, I have some file descriptors already. That's just by convention, there's 3 file descriptors whenever a process starts. So anytime you print the 3 file descriptors, so in the parent, it calls parent, which does nothing, exits with the return of 0. And then in the child, it goes ahead and just exec LP's uname without messing with the file descriptors at all. So it'll be the exact same terminal as what we originally started with. So it would just print out the results, the standard out, and we see it on the same terminal. Yeah.
So you're passing child 2 pipes, right? Or 1? You're passing child like a read and write pipe?
Yeah, but we haven't done anything with them yet.
Oh, okay.
So there's just placeholders, so I don't have to write code to make this faster. So we haven't done anything with pipes yet. Yeah.
Are file descriptors like virtualized, or are they like same across every single process?
So they just refer to something. So they're kind of like pointers.
But like the number 1 will always refer to the same one, no matter which process you're in.
No,
No, right?
no. Just by convention, it's just 0 is standard in, 1 standard out, 2 is standard error, and what they actually are connected to will change depending.
Does that have to do with like a child and parent hierarchy in some way, or?
No, it just depends what you want to do with it, because we're going to screw with them right now. Right, so what's working, uname is just outputting its answer to, it's just writing to file descriptor 1, like we saw in the beginning. So if I want to capture its output, what should I reach for? So I'm trying to communicate between 2 processes. So I probably need a pipe to communicate between them. Yeah? Wow, we're not awake today. Okay, so what is, so far we just forked. So ignore all the declarations. I just forked. We know what fork does. Creates a new process. So now after the fork, I have two processes. One's going to call parent, one's going to call child. If I am the parent one, it just does nothing. And then it would just return 0. It's donezo. It exited 0. If I'm the child, it's going to exec LP the argument, which in this case was uname. And then that's it. The child just becomes uname.
Okay, that makes sense.
But now I want to capture the output of the child
And put it into,
And-
do what with it?
and just read it in the parent process that created it.
So you can put it into file descriptor 0? No, 1, right?
Put into file, yeah, but put,
FD1, you're writing into that pipe.
okay, yeah, but first I need to create a pipe.
Didn't you already do that?
No, I just allocated space for them. There's no call to pipe.
Oh.
Okay, so first, so this is just an array declaration that just zeroes it out,
Okay.
if no one's read this syntax before. But, so I have these check error functions that essentially, check error just returns checks if the value is -1. If it's not -1, it means it's fine. And if it is, it's just going to print an error message and then quit out of the process. So this is just the sanity check because it might save our ass later. So we want to check error. We're going to call pipe. So we'll have a pipe that represents the output that we want to capture. So we just give it the array, and after it will set it for us. So we have this. So now after pipe, it's going to create 2 more file descriptors if it's successful. So file descriptor, it's going to use the lowest number. So we have the default file descriptors up here. And then it will create 2 file descriptors. So we'll have out pipe FD, which will be file descriptor 3. And that is the read end. And then we'll have file descriptor 4, which is out pipe FD, pipe FD 1, pipe FD. And this is the write end. Okay? So what also, yeah.
So effectively, all it's done is stored the number 4 in the first element, number 3 in the first element, and the number 4 in the second element of an array of integers.
Yeah, and the kernel create an internal buffer. So if you write to one, you can read it out of the other.
If you created another array, or just use the number because you know it's 3, if you just use that number, would it be the same thing? Or do you have to actually write to that specific array? Does your kernel care about that specifically?
It's just a number. If you can come up with the numbers yourself, then
Well, like you just did it here, right? You know it's 3 and 4.
yeah,
So you want always 3 and 4 because
it will. Yeah. So the process could, standard processes open like this with 3 file descriptors, but someone might be a jerk and whenever they forked and then exec'd you, they had like 10 open file descriptors.
Right, okay.
So I know because I'm launching it through my terminal and I know nothing screwy is going on, but you won't always know this. Okay, so so that's my pipe. Why don't I just pipe here?
Because then you have 2 different pipes, and they're not connected to something. No, you don't know the same values, because then you create 2 different pipes. One would be 3, 4, and then one would be 5, 6, right?
No. Close, close. Anyone want to correct? That was so close. So after the fork, they are the same. Yeah, and then after that, they're independent. They both call pipe. So each new process creates its own pipe, and they would get the same file descriptor numbers, but they would be different pipes. Yeah. So the child would create a pipe, it would get 3 and 4, and then the parent would create a pipe, it would get 3 and 4.
But the buffer is
What they would refer to different things.
Yes, they would be different pipes. So this way I have 2 pipes that I can't share anymore because I should have done it before the fork. And then if I move it up here, I have 1 pipe and both processes have references to it. Yeah.
So when you create like a file descriptor, like when you open up,
Mm-hmm.
it kind of gets stored somewhere in the process. Like I don't.
Yeah, it has like a file descriptor table.
Pointer.
Yeah, it has a file descriptor table, and all of them are essentially, the file descriptor table just has a bunch of pointers to stuff.
Right, right. So even when different processes have like the same number, it doesn't mean they're referring to the same file descriptor.
Correct. Yeah, it's just a table.
The table is different for them.
Yeah. Yeah, so if I, PID, what am I using? So for example, I think I showed this in another lecture, like you can see all the open file descriptors for a process just by looking at this directory. So for example, my shell had, at one point it opened 103 file descriptors. So it messed with a lot of stuff. Because they're broken. So they're different colors depending on what they actually refer to. So this one is like some file. This one's a socket. These are all shared memory that have to do with Chrome for some reason. And then it has its own status. But you can screw around with file descriptors. I think I showed it before, but that's neither here nor there. Yeah.
This is kind of like different question, but so you talked about how like you can mess around in kernel mode before. What happened? Like, can you ever touch the BIOS? Is that like totally different? Like,
That launches your kernel.
so you can't really touch. Can you ever touch that code then?
You can, but generally, if you like do BIOS updates, it's like EEPROM chip, and it takes a long time, and it's
Okay. So kernel mode doesn't give access to BIOS.
generally the BIOS just boots your kernel and then tries to hide itself.
Okay.
But you can interact a bit with it depending, but that's much more advanced. Okay, so now we have a pipe. So out pipe FD is correct. So if I want to capture the output for this process, it's writing to file descriptor 1. So if I want to capture it, I should probably make it write into the pipe instead of just whatever file descriptor 1 is. So how would I do that? So here's a hint. We want to use Dupe 2.
Is it similar to like the arrow thing in the terminal?
Yeah. Oh, this class is much more confused than the other one. Okay, here. I will write it and I will proceed if someone explains it to me. Or here, I'll make a pretty number. So what would that do?
That will change the standard L
Which is just a file descriptor that's 1.
to whatever is in the output pipe FD, so the input part.
Yes, so it's the right end of the pipe. So I'm trying to, in the child, I'm going to copy the right end of the pipe and replace and make file descriptor 1 point to the same thing as the right end of the pipe.
So now in the child, you no longer have access to the terminal as an output.
Yeah. So now I just overwrote because file descriptor 0 originally was copied from the parent and it was to the terminal, and now I just replaced it.
Damn.
Yeah.
So how would you like return access to the terminal?
Well, you only have 3 file descriptors, so we're just replacing it.
No, like, but how do you like get the thing back to type into the terminal?
Well, so standard error is still connected to the terminal, but in general, you lose it. Yeah, first.
So in this case, Dupe 2 would return the input of the pipe where you write data.
So Dupe 2 should return 1, because that's the new file descriptor it gave.
Which is the input of the pipe now.
Yeah, which now points to the right end of the pipe after. Yeah.
Couldn't you like use a regular dupe to create a copy of the standard output and then use dupe to overwrite that copy or something like that?
Yeah, but I only want 3 file descriptors when I launch this process just to be nice.
But doesn't exec make a new process?
No, it replaces.
It replaces.
The only way to make a new process is fork.
So it replaces, but like the table, it keeps that sort of file script table intact.
Yep.
Everything else gets thrown out.
Everything else gets replaced. So like if it's already has like the libc open and it uses libc, that won't get touched.
Oh.
And like some other things like that.
Right.
Yeah.
What is so the standard out is closing, so you no longer can talk to the terminal, and then it's setting the standard out to be the same as type 1, right?
Yeah, the right end of the pipe.
Okay.
So here, I'll go ahead, check for errors quick because we should always check for errors. So if I do that, it's fine. And now if I run it, what do I expect to see?
Nothing.
Nothing. Why?
Because it's writing to the pipe and you're never reading from the pipe.
Yeah, so I'm not reading from the pipe, so the data is going somewhere. I can't see it anymore. Yeah.
One question. So if you just keep like writing to the pipe and you don't read it, like would the first few values you write to just eventually just get pushed out?
That's up to the kernel. I think it would just give you an error eventually that you filled up the buffer, so it doesn't lose data. Okay, so everyone good with that? It's getting captured, it's writing to the right end of the pipe. Let's see what happens if we go to the wrong end. So if we connect standard out to the read end of the pipe, something very bad should happen. And there you go. Bad file descriptor.
How does it so what is it trying to do? It's trying to...
So it would be trying to write to the read-only end of the pipe, which you can't do. That's an error. So we can see that we're actually doing the right thing. So you should only write to file descriptor 0 and only read from file descriptor, only read from 0 and write to 1. Yeah.
So in this case, if you did printf in the child after you did that dupe 2, it's going to write to the pipe. And then if you did...
Yep.
Okay. That's so weird.
That's not weird, that's cool, right? This is how things work.
So then they're able to check like the write only and the read only because like making this new file descriptor is kind of similar to calling the open system call where you say.
Yeah, so it has permissions that the kernel keeps track of. So write only, read only. All right, so let's be good citizens here and close our file descriptors just to be nice and clean. Close. This? So I'm just closing, so I'm copying, making essentially, if I give them numbers, I'm making 4 and 0 point to the same thing. And then I'm going to close 3 and then close 4 because I don't need them anymore.
Because, so when you're closing it, you're just closing that specific file descriptor, but that doesn't mean other files refer to the same thing.
Yeah,
Okay,
in different processes too,
right.
because the parent still has file descriptors open.
But its pipes are the same, though, no? So you've also closed the parent's pipes.
I've closed a pipe that the parent has, but to close a pipe completely, every reference to it has to be closed. So the parent still has a reference to it.
Oh, okay. Okay.
So I guess like maybe like both have to be the same one as the pipe. One say close it out, the other one say the pipe is closed.
All right. Okay, so this takes care of the child. It's writing to the read end of the pipe, and it's not going to use it's writing to the right end of the pipe. So it's not going to use the read end of the pipe, and we already cloned it, so it's pointing to what we want it to point to, so we can close it too. We don't need it anymore. So whenever we exec LP, there's only the 3 file descriptors. So there's still only these file descriptors when it launches, except one, we replaced it with what was originally out pipe FD1. Yep.
So when you're closing a pipe, that only means that the numbers in that process are no longer valid?
Yes.
If you still have numbers that access that pipe from another process, they can still work?
Yeah.
Okay,
And that's why our terminal worked. So we cloned it, and then it printed to the terminal because we were sharing the same file descriptor. Okay, so it's writing to the pipe. How do I get data out of the pipe? And I probably want to do it in the parent. So how do I get data out of the pipe?
We just have to wait, don't we? Wait on the child process?
Oh, wow. Such a responsible parent.
But like we need to make sure that they do the write to the pipe first before we read from it, don't we?
Is read blocking or not?
Oh, I guess it is. I don't know.
So remember we wrote cat that just read and write? It just stayed there waiting for data if we called read.
Okay.
So we can call read. That's cool. So let's call read. So what does read need? Read needs a file descriptor, a buffer, and some bytes. Who wants to tell me how to create a buffer? Come on, I hit my head this morning. I don't know how to program. Help. A bunch of bytes. What's a byte in C?
Character.
Character.
Create a character array.
Create a character array. Buffer. I'll give you a good size. That size is really good. You'll see why later. So I'll create a buffer this size. Now I can do read, right, I think? So what file descriptor do I want to read from? What? Okay, so I want to read the data that the child wrote. So the child wrote to out pipe FD1. So it should pop out of the 0 side. Yeah. Out pipe FD0. And then I'll give it my buffer, and then size of buffer.
Do you not have to like pass the buffer to a void pointer or something like that, or no?
No.
Okay.
So that should compile. Oh, I'm missing a bracket. Thank you. Missing a bracket. So what does read return? Oh.
No, it should return the amount of bytes it read or.
Perfect. Yeah. Now, number of bytes it read or -1 if it failed. Bytes read equals this. And then I can check error because it's -1. So I'll check error for my read. All right, cool. So my parent process should have read from that. So if I execute it, what should I see now? Nothing again. But hopefully I read some data. So let's print it out. So this format specifier is going to be weird. Just trust me, it works. So how do I print off the data?
#S.
So did I read a C string?
Probably not.
No, I just wrote a bunch of bytes. So anyone who's advanced enough to tell me what I should put here? Come on, everyone should know this off the top of their head. There you go.
Wait, what? I'll write this down.
What? So that means, so this is a string, so there's still % string, but there's a dot star that's saying how many characters to print, and it gets the first argument. So bytes read is the number of characters to print, and then that's the array. So I don't have to give it, it doesn't have to be null terminated, I'm just printing that many bytes.
That would be so helpful.
No one's taught you this?
I've been trying.
No one knows this off the top of their head? Come on now. Yikes. All right. So if we do that, hey, cool. It outputs. And it outputs because in the printf, we didn't touch our standard out. So we're writing to our original standard out, which means we can see it on the terminal. But we wrote out the data we read from the process. So we communicated. We got data.
Except, isn't that the exact same thing as just typing in your name at this point?
Yeah, but what about if that process did something cool and you wanted to capture its output and do stuff? So for instance, what if I had to grade your programs? I'm going to run your program, and then maybe I parse some output from it, so I could just read output from it and do something interesting. So hey, that's how our grading works in the Python subprocess module. All right, any questions on that? Yeah.
So, but this method only works when you fork it, like
Yeah.
from a thing.
Yeah, because we're setting up the file descriptors.
Well, can you like do it sort of when you're not fork, when the two programs are not like fork?
But you can only create a new process from a fork.
Right.
So they're going to be created from a fork. Yeah.
Can you please explain the dot defined thing again? So it's like it's
So
specifying you have.
it's specifying how many bytes to actually print, and it takes the first argument. So instead of just a string, it takes a length and then the string.
So if it's like less than the buffer, it won't do that many.
Yeah, so if I just say, hey, print the first two characters, all right, that should just print li.
Like, wait, then.
What?
Why is there an additional line stuff?
So
No, why is there like additional percent sign on?
there's not. Oh, that? Oh, at the bottom? So the terminal will tell me if it doesn't end in a new line. Yeah.
Man, I'm confused. Okay. So in this case, if we did with this system, you didn't ever fork, then if you did what you did, then you would actually never be able to read out because you're overwriting standard output. So the only reason it's working is because you have two different standard outs, right? And we
Well,
overwrite one of them.
So yeah, in the child, I overrode it so that it went to the pipe instead. And in the parent, I never touched it.
Right, okay. But if you did it in the same process using those pipes, then you would never be able to output anymore because you've gotten rid of the standard output.
Yeah, I mean, it would just, you'd write into that and write data to yourself.
Keep
And
writing to the buffer.
yeah, which is kind of silly.
Okay.
Okay, let's do the other half. And we only have, oh God, we only have 6 minutes. All right, speed run. So let's create another pipe. In pipe. Okay, so now we have 2 pipes. So we want one that we send data to, and we already have one that we get data from. So our child's probably going to look more or less the same. Oops. So I will just replace out in. How did I do that? I'm cheating. Send it in file. Okay. So now I'm replacing this. So we sped run this. So now I'm replacing the standard in with the read end of the pipe. So now whenever it reads data, it's going to be reading from the read end of the pipe. So I need to put something into the pipe. So in the parent, the right end of the pipe is going to be in pipe FD 1. That's what I should write. So I said I wanted to write a message. So I wanted to write testing new line. So I want to write Message, Sterling, message.
How would the parent know that the thing it read was already, like, because we don't know if the child already, like, put stuff into the buffer.
What do you mean?
Like, when it puts the Linux into the buffer, like, what if, like, the parent reads before the child puts it in?
So it's just going to wait
Oh, this is,
for some data.
so this read will block, right?
Yeah. Okay, so now check error, bytes written. Holy, we're speed running now. Right. All right, so that should write some data to that process. So I think that's all we need. Yeah. So if we execute that, if we do uname, we should expect to see the same thing because it doesn't read anything from standard in. All right, just does that. So what reads something from standard in? Cat. So cat, if I hooked up everything correctly, which maybe I didn't, I should see testing. Hey, so there's the data I wrote into it.
Wait, so if it gets blocked, doesn't that mean that if you never write into the other end of the pipe, it's going to just constantly be stuck?
Yep. So let's see. Let's quickly be a very good parent. So you told me I should wait. Let's wait. 3 minutes. Jesus. So this is how fast you program your labs, right? Check error. Oops. Wait, PID. Whoops. All right, so we want to wait on it. Let's just write some asserts. WIF exited. Leave status. Let's just assert. And then in exit status, we should get its exit status because that's a good thing to do. W exit status. This is what we had before, and we'll just assert that exit status. What's good? Good 0. All right, that's what everyone was going to write? All right, let's run it now and see what happens. So what's happening?
Waiting indefinitely for something.
So we're waiting indefinitely, which means our cat process isn't exiting. Why would cat not be exiting?
Because it's waiting for you to write testing.
I already wrote testing. So I wrote testing to it, but it's still waiting.
Wait, can you go to the child? Where's the child?
The child's just executing the program. So what's happening, I'll give you another few seconds. So I wrote to its standard in. I wrote the string testing. It worked before. It was fine. I got it. I printed it out when it was done. That was fine. But now I'm waiting for it to die, and it's not dying. So why wouldn't it be dying?
Because it wrote to standard out and then which is out pipe and it's not being read.
Well, so essentially, cat's waiting to read more input, and more input is possible because we haven't closed the right end of the pipe. So it's still it's just waiting. It's possible it could get data. It's possible I slept for half a century and then I'm going to call write again. So what I should actually do is after I write to that pipe, I should be a good citizen. And this is why you should be a good citizen, because now I'm done with it. So I can close it, and that way cat will know that no other output's possible because no one has that file descriptor open. So
If you close it, if you need to use it in the future, how would you
you don't. Because it's closed, it means it's done, no more output. That's the only way cat.
how would you communicate with the process again in the future?
You can't. So I'm waiting for it to die, so I'm waiting for the process to end. How can I communicate with a dead process? So-
if you're not waiting, then like you can keep it open.
Yeah. All right, so if I do that, it works properly. Continue this on Discord or next class because everyone kind of looks confused.
I just failed at the term now.
All right, just remember I'm pulling for you. We're on this together.